So what is air? Air is a mixture of gases, a mixture, homogeneous mixtures of tons of particles of gas. 78% of it is nitrogen. Nitrogen, in the natural form, is found with two atoms of nitrogen combined together to form a molecule that has 3 bonds, and this makes it very stable. So you actually have that nitrogen in air that is there, but it won't really do anything to your body. We breathe nitrogen. We don't just breathe oxygen. How cool is that? Now, we also have oxygen, right? We have oxygen. Without oxygen in the air mixture, we could not survive. Humans would not survive. And that's actually one of the biggest issues about why there is not life as we know it in other planets. Because we need oxygen, and not all the planets will have that. So what makes the Earth so special, part of it is the air. And how the Earth has developed to where right now, the way we have it, it is perfect, right? So we're gonna have those, that composition, and we're gonna have traces of other gases. And then those traces are so important that they even define what we smell. So when you can smell a candle burning, when you can smell perfume, when you can smell something very stinky, when you can smell stinky feet, or when you can smell rotten food, all those are actually very small traces of particles in air. And then there are a big deal. We're going to learn about how those traces could either lead to health related problems, or it could just give us the pleasure of getting aromatherapy and enjoying smells, right? So but that's only traces of air, but mainly we got nitrogen and we got oxygen. Okay, now we're going to learn about how do we interpret those percentages, because we're often going to be asked about those percentages. About 0.0402% of air is carbon dioxide. When we think about carbon dioxide, we're saying that if we had 100 particles of air, 0.0402 particles will be molecules or atoms in air. That would be however many carbon dioxide molecules we have. It's kind of hard to think of it that way. When it comes to very small quantities, we don't really think of parts per hundred, meaning percentage, but we think of smaller concentrations, right? So we think of it in terms of parts per hundred. So if I look at this, I could say, well, it is 0.0402 parts per hundred, right? Per hundred. Or it could be 0.402 parts per thousand. And then 4.02 parts per 10,000. Or 40.2 parts per 100,000. Or 402 parts per million. So ultimately, all of these are just simply forms to talk about quantity. Now, if you were given, oh, well, this is 402 parts per million, it would be a more realistic way to understand this, and it helps to visualize this. So in that case, if we think of parts per million, or P m, we're going to say that for every 1 million molecules or atoms, we will find 4O2 carbon dioxide molecules. In a given city, the allowed or permissible limit of ozone, a contaminant, is 0.12 parts per million. But it actually is reported that the city is showing 0.14 parts per million. So the question is, by what amount in parts per million does the reported value exceed the permissible limit? So we're going to have that in that case, I got my 0.14 parts per million minus my 0.12 parts per million. I want to find the difference, right? So I'm going to find that it is going to be 0.02 parts per million. Now, what is that represented in the percentage? So it is 0.02 parts per million out of the 0.12 parts per million times 100 will give me my percentage. So this is very relevant because entities like the EPA, the Environmental Protection Agency, make sure that we set permissible limit for different contaminants and different particulates that if exceeded could become a high risk. So understanding what parts per million mean and how that is represented in terms of percentage is essential. Okay, so let's look at a different type of example, but okay, so let's look at a different type of scenario. If we have a percentage, how can we express this in terms of parts per million? So if you have 0.0041%, what is that concentration in parts per million? So this is parts per 100, right? Parts per 100, right? So if it is parts per million, 1, 2, 3, 1, 2, 3, that is 1, 2, 3, 4, 5, 6, right? 6 or equal 10 to the 6, right? 6 zeros. So we can just pretty much move the decimal places, the remainder of places. So I got 2% over here, so I already got those two, the 100, right? So I got 1, 2, 3, 4 extra places, so you can move your decimal place 4 spaces, 1, 2, 3, 4, and then we will find that it is 41 parts per million.